Now let us discuss the concept of AC drives. So basically the motor used in AC drives is an induction motor. In that also again the more popular motor is a squirrel cage induction motor. It can be either single phase or three phase. So first let us discuss what are the basic advantages of AC drives over DC drives. So these advantages list is important for objective exams. So we all know that induction motors are very robust in construction. Therefore, what we can say that AC drives are robust. Comparatively, DC drives, AC drives have less maintenance. Why? Because in case of DC drives, as the basic motor is DC motor, due to the brush contact on the surface of the commutator, continuously you have to clean it. It need more maintenance. Whereas in AC drives, it has less maintenance. And AC drives are more suitable in hazardous places or hazardous environment. So especially I can say like chemical and mining industry. Especially chemical and mining industries, these AC drives are more preferable. Okay, and comparatively DC drives, these AC drives are less weight for same power rating of DC drives. Okay, so these are some of the advantages of AC drives. Of course, every system will have its own limitations also. Disadvantages. So what are the disadvantages? In case of DC motor, the field flux and armature flux are decoupled. Okay, because the field flux can be controlled separately from another source. That type of control is not possible in case of induction motor. Because of that, speed control is somewhat difficult here. In case of induction motors or AC motors, we can say speed control is complex. Speed control is complex comparative to DC drives. Compared to DC drives. Therefore, design of power electronic circuit is more complex here. Design of power electronic circuits is more complex. Okay. So these are some of the limitations of AC drives. So from this topic also we can get questions comparatively DC motor or comparatively DC drives, AC drives have advantage and disadvantage. Some 3-4 statements can be given to you, and identify which of the above statement is correct or which of the above statement is wrong. These type of questions we can get it from this one. Whereas in our earlier topic DC drives, we can get for given particular quadrant of operation what type of power electronic converter can be selected, or a particular converter is given up to what power ratings we can use that particular DC drive. So generally drives questions we will have these type of questions only. Beyond that I don't think in AE and AEE exams we will get it. Okay. Now let us see what type of converters will be preferable in order to control the speed of an induction motor. So in order to get an idea of that, first let us look into basic equivalent circuit of an induction motor. Okay, so let me write down here per phase equivalent circuit of 3-phase induction motor. So probably in your induction machines class you might learn that what is the working principle statement of 3-phase induction motor. Just let me recollect once just for the convenience of understanding this particular topic. Suppose whenever a 3-phase balanced AC voltage is given to 3-phase distributed winding of stator of an induction motor, then what will happen? A rotating magnetic field will produce, right? So that magnetic field will rotate at a speed 120 F by P in the air gap, where that speed is called synchronous speed. Okay, so what are the key words in this particular topic that we need to understand? Synchronous speed. The magnetic field in the air gap will rotate at synchronous speed. You can define with Ns is equal to 120 F divided by P. This is in RPM, or you can convert this RPM into radian per second, where omega s in radian per second. Okay. Now when this rotor air gap field cuts the rotor windings, okay, then what happens? When the rotor winding has a closed path, some currents will start flowing in it. How the rotor winding will have a closed path? It can be short circuited by using end rings in the squirrel cage construction, and it can be closed through slip rings in slip ring induction motor. Okay, so due to the interaction between air gap field and the rotor currents, an electromagnetic torque will produce. Let me write down this statement here. Due to interaction between air gap field and rotor currents, an electromagnetic torque will produce. Electromagnetic torque TE will produce. So in this induction motor concept, the rotor will rotate at a certain speed. It will always try to catch up the synchronous speed. but it will never catch up. So with that point, a concept of slip will come into picture. We can define slip, S is equal to synchronous speed omega s minus rotor speed, you can also call motor speed, denoted with the symbol omega m divided by omega s. This is the definition of a slip. So from this, motor speed can be expressed as motor speed omega m can be expressed as synchronous speed multiplied with 1 minus s. Synchronous speed multiplied with 1 minus s. This is one of the important relation in induction motor topic. Now, just for more convenience, let us draw equivalent circuit, per phase equivalent circuit. This is a stator side resistance and reactance and magnetizing inductance XM, rotor side reactance and mechanical equivalent resistance from the rotor side. Okay, so here terminal voltage, let me call it V1, stator side voltage. At one particular instant of time, those are the polarities. Of course, it is a AC circuit. And here, this is I2, rotor current. Rotor resistance and mechanical equivalent resistance referred to rotor side, R2 by S. Okay, this is somewhat simplified circuit, equivalent circuit of three-phase induction motor with a little bit error, not much error. Just to simplify the circuit analysis, this magnetizing branch can be moved before the stator impedance. Okay, therefore we can redraw further simplified equivalent circuit like this. I just moved this magnetizing inductance branch before the stator impedance with a little bit compromising on the accuracy, not much, like this. Okay, now rest of the circuit analysis is same. This is R1, X1, R1, X1 and rotor side reactance X2 and equivalent resistance of the mechanical system in the rotor side, that is R2 divided by S. Now the rotor current, you can take it I2. Okay, so this is more simplified version of per phase equivalent circuit of three-phase induction motor. Now from this circuit we can define rotor current like this: stator voltage divided by R1 plus R2 by S plus Jx1 plus x2. In the phasor form, we can write it like this. And from the magnitude part, I2 magnitude, you can write it like this. V1 divided by square root of R1 plus R2 by S whole square plus x1 plus x2 whole square. This is the equation for rotor current. Okay. Now let us look into power developed in the air gap. Air gap power, let us denote it with the symbol PG. For the three-phase system, it can be expressed as 3 into I2 square into R2 by S. Next, rotor copper loss. Rotor copper loss PC is equal to 3 multiplied with I2 square into R2. 3 into I2 square into R2. Now, mechanical power developed. Mechanical power developed. PM is equal to PG minus PC. Air gap power developed minus rotor copper loss will give you mechanical power developed. So 3 into I2 square into R2 by S minus 3 into I2 square into R2. So from this we will get PM is equal to 3 into I2 square into R2 multiplied with 1 minus S divided by S. This is very important conclusion in induction machines class. Okay, I hope you are familiar with that. It's just repetition only. Now, what is the objective of doing these equations? We want expression for electromagnetic torque. Electromagnetic torque developed by the induction motor. PE is equal to PM divided by rotor speed in radian per second. So that PM is equal to TE multiplied with omega m. Now let us substitute. What we will get? TE is equal to, of course, 3 divided by omega m into I2 square R2 multiplied with 1 minus S divided by S. So 3 divided by what is omega m here? Omega S multiplied with 1 minus s into I2 square into R2 into 1 minus s divided by s. Okay. So here we can cancel 1 minus s and 1 minus s. Finally, we will remaining with TE is equal to 3 by omega s multiplied with, if you substitute I2 square, you can have V1 square divided by, where in the previous slide we had a I2 equation. If you square it, V1 square divided by R1 plus R2 by S whole square plus X1 plus X2 whole square. So this is a I2 square into R2 by S. Okay. So this is the equation for electromagnetic torque developed by three-phase induction motor. Okay, electromagnetic torque developed by three-phase induction motor. Now, if you draw this equation versus the speed, now let us see what type of curve we will get it. Let us look into torque speed characteristics. Torque speed characteristics. You might studied this topic in induction machines class. So we'll just draw the curve without much explanation. In fact, that is not in the scope of power electronics lecture also. So if you want more details, you can refer induction machines class. Here I will just draw what is this characteristics. Now here y axis I can take either speed or slip. X axis torque developed by the motor. Okay. So here how these torque speed characteristics looks like. So if the slip is 0 here, okay, and 1 here, that means this is the starting torque. This is a starting torque. So right, and this is maximum torque. Okay, and here This is slip at maximum torque. Probably you can learn equations for maximum torque, slip at maximum torque in the missions course. We will not go with that. And here coming to the speed point of view, starting rotor is at standstill, it is a 0, and this is corresponding to synchronous speed. So in this region, here in this region, the slip value is 0 to 1. You can also say that induction machine will operate in motoring mode when the slip is in between 0 to 1. So when the slip is between 1 to 2 or greater than 1, here in this region slip is greater than 1. This is called braking operation. Okay, induction machines course you might study it as a plugging operation also. So that is a braking operation. Whereas if the slip is negative, when the rotor speed is greater than synchronous speed, in that case slip is negative, that operation is here. Slip is negative or less than 0. This is generating operation. This is a generating operation. Okay. So basically this generating operation will be used in wind turbine applications. In the wind turbine, basically it will operate as a generator, because the speed, the power production in wind turbine applications depends on wind speed. Basically it is used as a variable speed generator. Okay, synchronous generator is not suitable for wind applications. Of course there is some exceptional cases like permanent magnet synchronous generator can be used in the wind turbine application, that is a different discussion, but most of the generators are induction generators, basically variable speed generators. So when the induction machine is used in a wind turbine applications, it will be operated with a slip less than 0. Okay, slip is a negative here. So in that case the machine will operate as a generator. Okay, so this is briefly the torque speed characteristics of induction machine. Now so with this basic, what is our focus here? So let us look into that. Speed control by variable voltage and constant frequency. Okay, speed control by variable voltage and constant frequency. First scenario. Now if you go back and see this torque equation, we can say that torque developed by the induction motor is proportional to square of the stator voltage. Therefore let us write down here TE is proportional to V1 square. Of course we are not supposed to apply more than the rated voltage to the induction machine, right? In that case what we can do, you have to apply less than the rated voltage to induction motor. In that case what will happen to the torque speed characteristics. Let us see. Now, just like earlier, I can take speed or slip on y-axis, torque on x-axis. Therefore, at rated voltage, this is how we will have a characteristics. Okay. Now, let me take first characteristics. Let me write down here. This curve 1 corresponds to at rated voltage. Anyhow, we are not changing the frequency at all. At rated voltage. Okay, at rated voltage. Say, if you reduce the voltage, stator voltage, because we are not supposed to increase the voltage, right? Therefore, if you reduce the voltage, then what happens to this curve? This curve will get shrink like this. Let me take second curve. Okay. So, curve 2 corresponds to at reduced voltage. Curve 2 corresponds to reduced voltage. So what is this curves are telling? You will understand more clearly if you superimpose load characteristics on top of this. Let me take here, this yellow curve is a load torque. So let me write down here, load torque, load curve, TL is proportional to square of this speed. Now here there is a very important point, follow carefully. If it is clear, it is a very simple concept. Suppose now observe carefully that yellow curve touches the first curve at one particular point. Okay, let me take here, let me use another color, blue color. So it touches at this point. Now this yellow curve, load curve, touches the second curve, means at a reduced voltage curve at another point. Okay, therefore let us use some names here. I think yellow is more visible. Let me take, this point is A, this is B, and this is C. So what is the speed at rated voltage? Speed at rated voltage is equal to AB, I can say, right? Speed at reduced voltage, speed at reduced voltage is equal to AC. Speed at reduced voltage is equal to AC. Observe carefully, the variation between AB and AC is very small. Okay, so what we can say that this type of control, right, voltage control will give voltage control will give very narrow range. Voltage control will give very narrow range of speed control. Why? Because when you observe here, the load torque operating points AB and AC, okay, the difference between AB and AC is very less. Voltage control will give very narrow range of speed control, okay. So voltage control is not preferable for the applications wherever wide range of speed control is required. It will give you narrow range of speed control. That is why this type of control is more popular in the applications like fans, more popular in fans. This is the basic reason in our household applications, when we are using fans, we will use AC voltage regulator. What is the purpose of AC voltage regulator? If you recollect our previous lectures, AC voltage regulator will give variable voltage at constant frequency, okay. So more popular in fan type of applications. So if you see the power electronic circuit, that will give you this type of output. Say for example, this is an induction motor. One of the basic device that will give is a triac, or you can also say that single phase AC voltage regulator, okay. In case of single phase AC supply, you can draw this circuit with a triac. This is an induction motor. So this is the power electronic circuit that will give you voltage control. Suppose if you look into the three-phase circuit, if you look into three-phase circuit, three-phase induction motor. In each phase, you can use one AC voltage regulator, three-phase system A, B, C, two thyristors, anti-parallel connections. So these type of circuits will be used to control the speed of induction motor in the voltage control method, okay. So you can say that this is a voltage control method. Voltage control method. Now the second way of controlling induction motor speed is by, let me write down like this, speed control by varying frequency and constant voltage. Constant voltage. Now if you see the EMF equation of three-phase induction motor, we can write it like this. V1 is equal to root 2 pi F flux into number of turns, let us use another symbol, T into winding factor. I don't know what symbols you learned in induction machines class. The point here is the EMF equation can be expressed like this. V1 is proportional to frequency multiplied with the flux. Say for example, if frequency is decreased, if frequency is decreased, then what will happen to the speed? Speed also decreases. Okay. So in that case, now observe carefully what will happen. We are maintaining stator voltage to the induction motor is constant. By maintaining the stator voltage is constant, and if you decrease the frequency, then what happens to the magnetic flux? Flux will increase. Flux will increase. Therefore, when flux increases, it will create saturation of the core. It will create saturation of the magnetic circuit. Therefore, remember, in the induction machine applications, when the stator voltage is maintained constant, you cannot decrease the frequency. Okay, this method you have to avoid, because it will create the saturation of the magnetic system. Now, suppose on the other side, if frequency increases, okay, then what happens? If frequency increases, speed also increases, right? Speed also increases. In that case, what happens to the flux? Flux will decrease. Okay. In that case, flux will decrease. Therefore, no saturation in this case. No saturation. Okay. But this type of method, say for example, in case of DC motor, in DC motor, in the field control method or flux control method, we have one concept called N is proportional to EB by phi, right? Suppose here, by maintaining the terminal voltage to the motor is a constant, if you decrease the flux, speed will increase. Okay. If you decrease the flux, speed will increase. Exactly similar situation is replicated in induction motor. By maintaining the constant voltage to the stator of the motor, if you increase the frequency, then flux will decreases, so that speed increases. This particular concept, you can also say that field weakening method similar to DC machines. Field weakening method. Field weakening method. Okay. So, in case of constant voltage method, you have to increase the frequency, but you should not decrease the frequency. In this type of control, what type of torque speed characteristics we will get? In this case, we will get a characteristic something like this. So, y-axis speed, x-axis torque. Okay. This curve 1 belongs to curve 1 belongs to rated frequency. Okay, say for example this is a synchronous speed, right? Now when the frequency is increased, then what happens? The second curve I am drawing, speed will increase, but at the same time the curve shrinks like that. The orange curve that belongs to reduced frequency. Let me write down here, curve 2 increased frequency. Increased frequency, right? Now, one of the important property in these two methods, this is a torque speed characteristics in case of only voltage variation, but frequency is a constant. What happened here? The maximum torque developed by the machine reduces. Okay, say for example here, this is a maximum torque in the first scenario, this is the maximum torque in the second scenario, it is reduced. So when you observe carefully the concept, when you change only voltage but not frequency, maximum torque developed by the machine reduces. Exactly, when you change only frequency but not the voltage, in this case also the maximum torque developed by the machine is reduced, right? So these are the two basic limitations of these methods. This is TEM1, TEM2. So what we can conclude here, if we change either voltage alone, or if you control either voltage alone or frequency alone, either voltage alone or frequency alone, then what happens? Maximum torque developed by the motor, will decrease. Okay, so the point here is, in order to maintain almost approximately same maximum torque developed by the machine, what we need to control? That is the next question. In order to control or in order to maintain this approximately constant maximum torque, instead of changing voltage alone or frequency alone, you have to control flux in the machine. Okay, so next method, speed control by flux. Speed control by variable voltage and variable frequency. Variable voltage and variable frequency. Okay, so in this case, why we need to control both voltage as well as frequency? Let us see. By controlling flux in the machine we can maintain maximum torque developed by the motor approximately constant. We can maintain maximum torque developed by the motor approximately constant. Now the next question, how can we control the flux in the machine? So from this previous equation you can say that V is proportional to F into phi. In other words, flux is proportional to V by F ratio. Therefore, in order to control the flux, you should control both voltage as well as the frequency, but not only one parameter. If you control both the parameters, then you can maintain the flux in the machine approximately constant. Therefore, we will have torque speed characteristics like this. This is a speed and this is a torque. Okay. So here at rated operating conditions, this is how the curve is. By changing both voltage as well as frequency, you will have the characteristics something like this. Now the next question, see here, white curve corresponds to rated conditions. This is a synchronous speed. Okay, this curve corresponds to rated conditions. Now in this case, even if you decrease the flux, if you decrease the frequency, simultaneously you are reducing the voltage also, flux is almost maintaining constant, so that torque developed, maximum torque developed by the machine is approximately constant. Of course, there will be a slight variation, but that variation is almost neglected. Now the next question is, how can we get V by F ratio to be controlled? Suppose if this is an induction motor, like 3-phase induction motor, you can control both voltage and frequency with a circuit called 3-phase voltage source inverter. With a circuit called 3-phase voltage source inverter, we can control both V and F. V by F ratio can be variable. Okay. So in this way you can control the speed of induction motor, right? So the methods discussed so far, they are applicable for squirrel cage induction machines. Now there is another concept called for the slip ring induction motor. First let me draw the scenarios. Let us say 3-phase slip ring induction motor, and this is 3-phase grid. Okay, this is a 3-phase grid. So what do you mean by this? Stator is connected to 3-phase grid directly. Okay. Now rotor is also connected to the 3-phase grid, but through two power electronic circuits. Okay, now follow carefully here. Rotor is also connected to grid, but it is through two power electronic circuits. So let us say here this is a AC and it is a DC, and here it is AC and this is a DC. There are two converters, right? And what is this motor? Slip ring induction motor. Slip ring induction motor. Let me call it, this is a converter 1 and converter 2. So if this combination converter 1 and converter 2 is these converters, if you use these converters, 3-phase full converter plus 3-phase diode bridge, 3-phase full converter and 3-phase diode bridge. This is one possibility, and another possibility is both the converters, both are 3-phase full converters. Okay. So in the first scenario, this is called Cramer's drive. This is called Cramer's drive, and this is called Scabious drive. These are the scientist names. Okay. So under what conditions we can use these type of systems? In this case, Cramer's drive is preferable to control the motor below synchronous speed, whereas the Scabious drive is used to control both, above synchronous speed and below synchronous speed. Okay, so this is the concept called speed control of slip ring induction motor in case of by using these converter circuits. Now the more important point is this Scabious drive is popularly used in wind turbines, and that particular machine is called doubly fed induction generator, DFIG, doubly fed induction generator. Why doubly fed? Both the stator as well as the rotor are connected to 3-phase grid. Okay. In this Cramer's drive, the power flow direction is only one direction, whereas in the Scabious drive, the power can flow in both the directions. Okay. So this is about speed control of induction motors by using various methods. So in a bigger picture, what you have to remember? In the bigger picture, you can remember like this: speed control of variable voltage and constant frequency, that is one method. Second method, speed control by varying the frequency alone. The third method, both voltage as well as a frequency. These three methods are applicable for squirrel cage induction motor, whereas coming to slip ring induction motor, Cramer's drive and Scabious drive. Okay. Now let us take a few problems. In a 3-phase inverter fed induction motor drive, the total harmonic distortion is 5%. If the maximum value of fundamental component of load current is 8 ampere, determine the RMS value of net harmonic current. So first let us look into that. So what is given in this question? Total harmonic distortion is given that In other words, 0.05. And maximum value of the fundamental component is given 8 ampere. Now the question is, what is the net RMS value of net harmonic current? So from this, what is RMS value of the fundamental component? 8 divided by root 2 ampere. Therefore, now answer for the first question. If you look into the basic definition, THD is equal to RMS value of the harmonic current divided by RMS value of the fundamental current. Therefore, you can express RMS value of the harmonic current is equal to 0.05 into 8 divided by root 2. Okay. So what is this value here? Let me simplify. 0.05 into 8 divided by root 2. This is 0.2828 ampere. Okay. Next question. B. RMS value of current drawn by the motor. So if you look into IH, RMS value of the harmonic current is equal to I square minus I1 square. Okay, I square minus I1 square. Therefore, from this, how to express this IH square plus I1 square under root. So IH square is 0.2828 whole square plus I1 square 8 by root 2 whole square. This value is 8 by root 2 whole square plus 0.2828 square under root 5.66 ampere. Okay, 5.66 ampere. That is the answer. Let us look into the next problem. This problem is another interesting concept. A 3-phase 50 Hz square wave voltage source inverter feeds a 3-phase 4-pole induction motor. The voltage source inverter line voltage has dominant fifth harmonic component. If the operating slip of the motor with respect to fundamental component voltage is 0.04, now the slip of the motor with respect to fifth harmonic component. Now let us try to solve this problem. So first let us define slip corresponds to fundamental component. Let me use a symbol S1. So what is the definition? Synchronous speed minus rotor speed divided by synchronous speed. This value is given 0.04. So from this, what you will have, 1 minus omega m by omega s is equal to 0.04. In other words, omega m divided by omega s is equal to 1 minus 0.04, 0.96. Okay. Now let us keep this value. we will use in the later steps. Now follow carefully here. If you relook into the slip definition carefully, the definition of a slip is like this. Slip due to nth harmonic omega s omega m divided by omega s. Follow carefully here. So inverter circuit is supplying voltage to induction motor, means what is that harmonic? These harmonics are corresponds to time harmonics. Okay. So in the missions class you might learn there are two concepts of harmonics. One is a time harmonic, another is slot harmonic. When it is a time harmonic, what you have to do, you should multiply the synchronous speed with respect to the number corresponds to that harmonic component. Okay. So that is n here. And the rotor speed, mechanical speed, basically it cannot change instantaneously. Okay. And here you have to use symbols like this, minus and plus. Under normal definition of slip, what symbol we will use? Minus, right? That means the slip corresponds to fundamental component belongs to minus symbol. So let me write down here, where in this formula, where minus is for forward field, forward field. So what are all the components that will produce forward field? They are fundamental component and 6K plus 1 harmonics. Those are 7, 13 and so on. Okay. Next one, minus for backward field, minus for backward field. Probably if you recollect a rectifier concept, due to 6K minus 1 harmonics, phase sequence will be negative. I explained in the rectifier chapter. Due to 6K plus 1 harmonics, the phase sequence is a positive, same as the fundamental component. So whenever phase sequence is negative, it will introduce magnetic flux that will opposite to fundamental speed or fundamental rotation, we can say. So what are all the components that will have this plus symbol or backward field? So backward field components are 6K minus 1 components, 5, 11 and so on. Triple N harmonics are absent. I am repeating here. In the slip definition, you should use minus symbol for forward field. What components will produce forward field? Fundamental component, 7th harmonic, 13th harmonic and so on. You should use plus symbol for backward field. What are all the harmonics that corresponds to backward field? 6K minus 1 harmonics. Now our question is, find the slip corresponds to 5th harmonic component. 5th harmonic component. So S5 is equal to 5 into omega s plus omega m. Why I am using plus here? Because 5th harmonic component will produce backward field. Denominator 5 into omega s. So if you cancel the terms, you will have 1 plus 1 by 5 into omega m divided by omega s. So this will give you 1 plus 1 by 5 into 0.96. Okay. So that is 0.96 divided by 5, 0.192. Therefore, for this problem the answer is 1.192. So this problem is very important, and another way of justification here, the phase sequence due to fifth harmonic component is a negative phase sequence, right? Now if you recollect from the missions class, whenever the phase sequence is changed, the machine will operate in a plugging mode, right? Plugging operation or braking operation, phase sequence will be negative. So in the braking operation, what is the slip here? The braking operation, the slip is greater than 1. So you can also say this braking operation is possible during negative sequence, negative phase sequence. So coming to harmonics, fifth harmonic component will introduce negative phase sequence. That is why we got our answer greater than 1. Okay. Now exactly in this concept, there was one problem given in the recent exam, NPDCL exam. Now observe carefully, just a theoretical question but conceptual question. A three-phase induction motor is fed by three-phase inverter having fundamental and all odd harmonic voltages without third harmonic. Without third harmonic means, what is the meaning? Lowest harmonic is fifth harmonic. Lowest harmonic is fifth harmonic. So due to fifth harmonic, phase sequence is negative. Phase sequence negative means the slip will be greater than 1. The slip will be greater than 1. So like that, strictly speaking, this is a missions question. But generally, we will feel that the word used three-phase inverter, it belongs to power electronics and the drives question. But my sincere suggestion, if you are very strong in missions concepts and three-phase power electronic circuits, if you understand the question clearly, no need of drives knowledge. So basic from missions concepts and power electronic circuits understanding, you can answer these type of questions. Sometimes people will feel V by F control also, it belongs to very advanced question. It's not like that. So you just try to understand the concept. This question was given in very recent NPDCL exam. This is what speed control of induction motor concept. So with this, I would like to conclude this drives lecture. Thank you. I wish you all the best.